much to the Colloquium here in Heidelberg. It's my pleasure today to introduce Enrico Ramirez-Ruiz from Santa Cruz. And I've just looked at his CV a little bit. It's very funny. So he's going to tell us how you do black holes with Hubble, of course, as it's standing here. Right? But he did his PhD in Cambridge, and under his lots and lots of fellowships, like the Mexican Academy of Science, the Calvi Fellowship, the Chandler Fellowship, and now currently he's holding the Packard Fellowship for his group. And he's, of course, faculty at Santa Cruz. It's also a very interesting one, the Silicon Valley 40 under 40 Fellowship. So, you know, if you ever get to Silicon Valley, you know one of the 40 most interesting people in Silicon Valley, apparently. And with that, I just, remembering of you, would like to welcome you to the stage, and welcome.
Thank you so much. Can we dim the lights a little bit? Thank you. It's a real pleasure being here. So I'm going to talk a little bit about, I think, a field that is emerging that basically relates to this idea that we can actually use the tidal disruption of stars in the center of quiescent galaxies to actually probe the existence of black holes in this system. A lot of the talk will contain actually work done by my grad student, James P. Sean, who's done amazing work on the subject, and he's now moving to Harvard as an Einstein Fellow. Morgan McLeod, who's also a grad student at UC Santa Cruz, and Heike Manukian, who's actually an undergraduate at UC Santa Cruz. So let me start, and I'm going to give you a little bit of a motivation of why you should care. Well, you know, we're really interested in this idea that every host galaxy, or every galaxy hosts a supermassive black hole in its center. And the problem is, of course, that current signatures for the presence of supermassive black holes are biased to the more massive galaxies, which, of course, in terms of the black hole demographics, are thought to be the minority of, you know, the massive black holes. So we can test the existence of black holes by, of course, looking at the gas and stellar kinematics, and of course we have the well-known M-sigma relation here. And even though heroic efforts have been made in systems which have velocity dispersions of only tens of kilometers per second, it's actually very, very difficult to really find these objects in the systems. You can also look at the digestion of surrounding matter, but as you know, the limit imposed by the balance between gravity and radiation pressure tells you that these objects are Eddington limited, and therefore the more smaller counterparts are lower luminosity, and therefore you can only see them to a smaller volume, and then nature doesn't help because the majority of local black holes are in fact inactive. Yeah? So you cannot see them from very far away, and in the volume that it's available to you based on this luminosity, they're basically all inactive. So if they're all inactive, how can we find them? And this plot I really like. It shows, this is if you extrapolate the M-sigma relationship to all galaxies, you can see here the demographics of these smaller mass black holes. They certainly dominate in terms of, not only in total number, but in terms of mass. This is if you only take early type galaxies. And if you look at the number of active AGNs in the local universe, you realize by every active galaxy that you see, there's about 200 or so, black holes that are inactive. And the key is, can we find black holes below, say, 1 million solar masses? And I will argue that, in fact, tidal disruption is actually biased towards these smaller mass black holes. So if they're quiescent, how do we see them? And for 2 decades, this tidal disruption of stars, and I'll go into detail about what I mean, has been actually put forward as a way to find these objects. And you can also inverse the question and said, well, we actually infer the presence of the black hole by looking at the stellar distribution. So we know the stars are there. Based on the stellar distribution, we know how often the star can actually get disrupted, and can we basically say, is the answer of the tidal disruption rate consistent with every single galaxy hosting a supermassive black hole? Now, the problem in trying to address this question effectively is, how does, after you digest star, the black hole turns on, and what's the luminosity? How mass is effectively converting to energy. And the key, as you will hopefully realize after my talk, is what happened to the debris of the disrupted star. So the questions that I'm going to focus on, I'm going to try to talk about understanding tidal disruption in the nonlinear regime, basically when the perturbations are comparable to the size of the object, and demonstrate that, in fact, these require the use of numerical simulations. This is a solar mass star going too close in a black hole of the mass of the galactic center. Then I'll talk about understanding the structure of the unbound debris. So when in a full disruption, about half of the mass goes above the escape velocity, half of the mass actually is bound. As you know, the center of mass, if there's no energy exchange, will follow a parabolic orbit. And we really want to understand the structure of this debris that is actually ejected. We also want to understand how mass is actually returned into the vicinity of the black hole, that mass that is actually bound into the black hole. And more importantly, are we modeling the accretion disk correctly after this mass falls back into the black hole and fuels a tidal disruption flare? So this is overall sort of the grand scheme of what I want to talk about. And I'm going to start telling you about tidal disruption physics. I'll tell you about the importance of hydrodynamical simulations. I'll tell you about adventures in the nonlinear regime and actually how these simulations are actually teaching us something new that we didn't know, trying to understand tides in the nonlinear regime. And I'll talk about calculating the mass heating rate. And thankfully, this field is no longer a theorist's imagination, but in fact, we have actually the first discovery for pan stars of what we really believe is a tidal disruption event with an extremely well-sampled light curve. And I'll try to basically convince you about how the constraints of these observations put in both disk assembly and the unbound debris. And I'll try to actually convince you that these systems are extremely interesting because what you're seeing is a broadline region being born in real time. Yeah? And how the broadline region from these tidal disruption events that you see being built in real time is very similar to that you see in AGNs, which are actually basically active for a long period of time. So, as you all know, the Earth basically changes in radius by 1 part in a million because of its interaction with the Moon. Yeah? And in that case, when tides are weak, we can basically assume that the tidal force is basically constant across the system, and trying to do perturbative linear understanding of these works relatively well. Now, what we're extremely interested in this case is, what happens when the tidal forces are not weak, and basically the tidal oscillations are comparable to the size of the object. And first, the object starts shedding mass, and second, if those oscillations are very strong, it will lead to a full disruption of the object. And even though analytical solutions exist, and this is a classical paper by Press and Tulkowski, in which they actually decompose the tidal field into spherical harmonics. They assume a sphere and they look for those basically non-radial oscillations, the energy carried by nonlinear oscillations. These basically eventually break down when the size and the structure of the object changes from being a sphere. And therefore, we have to resort to numerical simulations. There's been 2 types of efforts carried. Our group has been involved in both of them. One is to do it in a Lagrangian code like SPH, in which basically you're following in the fluid motion. And the other one is actually to do it in an Eulerian frame. And a lot of the calculations that I'm going to show you are in this frame. So just to get you acquainted, when I show you a box, the star is basically in the middle of the box in the center of mass, and the black hole comes in a parabolic orbit towards the star. Yeah? So as you can see here, the location of where the black hole is pointing changes as a function of time within the box. Yeah? So this is a kind of a visualization of what's happening in the sphere of influence of these black holes. So the orbits of the star follow these very complicated orbits because they're influenced not only by the potential of the black hole, but the potential of the other stars. Yeah? And in fact, what they're doing is they're doing a random walk in angular momentum. Yeah? And there's a probability that one of these strong encounters will send one of the stars into a radial orbit, which is called a radial lost cone orbit, and it gets very, very close to the black hole. And those are basically the events that we're more interested in. And if you ask, well, how close does a star has to get to a black hole for it not to longer be treated as a point mass, such that the tidal effects are important? This is what we define as the tidal radius, and this, of course, when the tidal force become comparable to the binding energy of the system. Now, if you think about it, what we care is the gradient of the force across the object. The gradient of the force across the object goes as 1 over r cubed. So virtually, the tidal radius, you can think of it as, I take the mass of the black hole, I spread it over a virtual sphere, and when the average density of that virtual sphere is comparable to the average density of the star, that's what defines the tidal radius. And it's very, very similar to the Roche log radius, but of course, this is defined for a parabolic orbit rather than a circular orbit. Okay? And this basically has this form here, which of course depends on the average density. So it has a relatively weak dependence of the black hole mass and the stellar mass, and a strong dependence on the size of the object. So what happens to the star? So the star falls in. I'm going to be using actually quite a bit what I call this beta parameter, which is the penetration. And this is basically the pericentric distance at the bottom and the tidal radius. So when beta is large, that means that you're going deep into the gravitational potential. When beta is basically small or weak, that means that they're basically weak encounters. I just collided with Hubble. So you basically develop this quadrupole distortion that at the tidal radius reach an order of unity. Yeah? And basically the resulting gravitational torque starts moving the object close to its rotational angular velocity. And it's both the bulge distortion of order unity and the large surface velocity that conspire to break up the star. So how often this happens? Well, as you know, the black hole dominates the stellar dynamics in a sphere of influence, which is basically given when basically the orbits of the stars are basically larger than that of the velocity dispersion. You can define the sphere of influence, which is basically the scale at which the black hole dominates a mass in stars comparable to its own mass. And in the galactic center, this is of the order of about 1 parsec. And then you can ask, well, what is the cross-section, the interaction cross-section? The frequency of interaction depends on the number and density of stars, on the cross-section, and on the velocity of the stars. And here, because you're actually going really deep into the potential, you're in the gravitational focus regime, so the cross-section is no longer dominated by the geometrical cross-section, but by the gravitational focus regime. And that allows you to write a rate in these simple terms. And then if you can relate basically with using the m sigma relationship, the mass of the black hole and the velocity dispersion, you can basically get a rate as a function of black hole mass. And just to give you a feeling, a star gets unlucky by interacting with others and getting these Radulov orbits, about 1 every 1,000, a few thousand years per galaxy. And of course, these very much depends on the structure of the stellar profile. So this is sort of an interesting order of magnitude estimate. Now, there's something extremely interesting that makes tidal disruption biased to lower mass black holes. And the reason is the following. So the Schwarzschild radius grows linearly with mass, while the tidal radius only grows as the 1/3 power. Yeah? So what happens is the black holes become actually progressively larger, their average density, if you think of it, basically decreases, and at some point, as a main sequence star is no longer disrupted by stellar mass black hole. And you can see here, this is sort of the menu of stellar digestion by black holes, and main sequence stars, basically once you get above 10 to the 8, they're basically swallow whole. They're basically disrupted inside the event horizon, and you really have to look for evolved stars for more massive black holes. In addition, these random walking angular momentum for the larger black holes, which have very long relaxation timescales, basically makes it much more difficult to send stars in these radial orbits. And as you can see here, not only the main sequence stars drastically decrease, but the rate also decreases. So as you can see, you're very, very biased towards these black holes, which are already difficult to find. So that's a nice complementary property of the systems. Now, in addition, when people always think about tidal disruption,
not that biased. I mean, I know 10 to the 8 rates of factor pretty small.
the rates are, but the number density of these objects, is of course much smaller. Now, the number density of black holes is 10 to the 8 compared to 10 to the 6.
Well, we don't know the number density of 10 to the 6. We don't know if
That's right.
they're black holes in such galaxies.
That's right. But if they were, they will dominate the tidal disruption rate. That's my point. So you can turn the question around.
Why not focus your efforts at 10 to 8 or 10 to 7 on places where you know you're black?
Oh, we basically focus on, we just completely unbiased. We basically just look all sky surveys and see where these objects come. You know? So when people think about tidal disruption, they always think about the full disruption of the stars. And actually that's not true, because in fact, the majority of tidal disruptions are weak interactions. Yeah? And even if you go at the tidal disruption radius, because the average density of the sun is not representative of the entire profile, the core of the sun is certainly much more dense, what ends up happening is that you ultimately get a surviving core. And the majority of tidal disruption are these partial disruptions in which the survival core is actually left, and the surviving core is actually going to play a key role in determining the energy of the material that is both unbound and bound. Yeah? So you can think of it as a reduced three-body problem in which you have two tails and a core. So what I'm going to show you here is a partial disruption of beta of 2, so you're going twice as deep to the tidal radius. This is a star-like or sun, getting disrupted by 1 million solar mass black holes. As you can see, you have strong mass sharing in the Lagrangian points. What you see is that part of the material that is ejected in both tails actually comes back and it starts exciting these spiral mode features, which actually inject a huge amount of energy into the star. I call these stars phase lifting of stars because you can take an old star and make it look much younger. The diffusion timescale is about 100,000 years. So these stars would actually look much younger for about 100,000 years. And if you multiply that by the event rate, you expect to see about 10 or so in the galactic center, which are thought to be more massive than there actually are. Yeah?
Enrico, can I ask about the simulation? That's, I presume, projected density temperature
That,
line.
this is basically temperature.
It's temperature.
Yeah. This is there's a constant temperature. So what you're seeing here, this is density profile, and we're basically making constant temperature. Yeah. So this material is basically very, very cold. And then we basically, because this fluff goes very high, we really want to give you an impression of where the photosphere of the system is.
But how do I read off this plot? How much brighter the whole affair gets from this?
Oh, from the luminosity. That's hard to do because, of course, you have to rely on the diffusion time scale of the material. So I should show you a plot of what tau is. But if I show you a plot, it will look like, it would start like about 1,000 times the solar luminosity. And then it goes up, and in about 1,000 years, it starts decreasing, and it goes back to its main sequence star. And not quite its main sequence star, because its actually average molecular weight has changed. But I can show you a plot of one.
But even if it gets 1,000 times brighter, that effect itself is not observable.
Not when it's the brightest, because the event rate makes you that you will see them in a hot state not very often.
How fast is the remnant here rotating?
So the core is actually rotating very close to breakoff, like 0.8 or something like that. So there's the issue that if you're able to tap into the rotation of the core, then you can make these systems actually appear hotter for longer.
Well, I was also wondering if that's an observational signature at later times where you have enough accretion material.
That's right. So you can, in principle, mimic sort of a larger surface gravity just by rotation. Okay, so just to give you a feeling that we're doing things correctly, I'm going to show you this plot. So here I apologize, I'm using 1 over beta instead of beta. But basically, the tidal force gets stronger as you go in this direction. So this is the standard Presental-Koski formalism, and it makes sense that basically the energy stored in the oscillations increases as you get closer and closer to the tidal radius. Yeah? So we want to see how close we are in this prediction. So we clearly see the L equal 2, M equal 2 mode, which is basically the quadrupole mode. That's where most of the energy is carried. You can see it clearly here. Then you say, well, how well are you doing? So something that you should notice is that you should not believe our simulations, for very, very weak encounters. Why? Because that means that the average distortions are smaller than the size of our grid. Yeah? So we're basically over-predicting the energy deposition, and you can clearly see this in this. And we have done these both with SPH and grid code, so we get more or less the same result. So I want you to bear with me in this plot, which is actually interesting. So this is not a star, this is a planet. This is a hot Jupiter being tidally disrupted by a planet. So the hot Jupiter is initially in an eccentric orbit. Yeah? And this is what I'm going to illustrate why this non-linear regime is quite interesting. So initially, this is basically the ratio between the initial energy of the orbit and the actual energy of the orbit. And as you can see, you start basically dissipating the energy. What happens? And this is what you always are taught in tides. The object becomes more bound. Why? Because where the energy comes from the tidal disruption, it comes from the kinetic energy of the orbit. You're sinking energy from that. But then, as mass shredding starts being important, look at what happens to the orbit. It goes from actually being bound to unbound. Yeah? And when we first saw this, we thought we were doing something wrong. And the argument, and as you can see here, this is a hot Jupiter basically being disrupted. And here, it's a little bit deceiving because since we have a cut in density, the tails seem to be actually shrinking, but in reality they're not. So what happens? Well, the mass shredding in the outer Lagrangian points is actually not symmetric. Yeah? And therefore, that leads to a kick of the center of mass. And you actually can make an object, once strong mass shredding takes place, to actually be ejected from the system. Yeah? And we actually have done this analytically, and we have actually proven that in fact this is the case, and it has to do with the difference between the quadrupole and the octupole. Yeah? Actually, are the octupole differences that make you that mass shredding difference that give a rocket effect. And what is interesting is that rocket effect is comparable to the escape velocity of the object. Yeah? So if you go extremely deep and you say shred 2/3 of your mass, actually the core gets a kick. Yeah? And we call this turbo velocity stars because they're not quite hypervelocity, but they get velocities of 500 kilometers per second. So they're not only hot, but they're also ejected not from the galaxy, but from the sphere of influence. So what we have done is we really wanted to understand systematically the tidal disruption of main sequence stars. And what I show here, this is for a gamma 4/3 polytrope, which gives you the right structure for the sun. And as you can see, this is as a function of beta. So what you see, initially the effects are weak, the mass sharing is weak. And as you go, you start shedding more mass. There's an interesting boundary here in which the star survives and the star is destroyed. And as you know, the star gets progressively more elongated. As you can see here, there's basically the limit of survivability does depend on the resolution. So one has to be careful, but this shows basically within our resolution, where actually self-gravity is able to reform the core, while in this case it's not. And this is clearly where you have the difference between a full disruption and a partial disruption. So what do we do? So people, what they want to know is, in the material that is actually unbound, what are the properties of this? And the material that is bound is how long it takes to go back to the black hole. Okay? And this is a simulation of a full disruption. As you can see, the initial size of the star is here, and we have let it go until hydrodynamical effects are no longer important. Yeah? So then people think about it, you have a collisionless problem. So basically, this is the most deeply bound material to the black hole, and you calculate basically what is the time scale for that material to return to the black hole. Yeah? So when people usually talk about the mass speeding rate, they tell you about what's the time scale for the material to return to pericenter. So how we do this? Well, you want to get the mass return, so you can divide this in the chain rule. And the key is basically, what is this value? So this is the specific energy per unit mass across the remnant. And this is, of course, determined by the hydrodynamics. And dE dt, you can just use Kepler's law. Yeah? And that tells you if a particle has a given energy, you know its orbit, basically. And Martin, in 1988, just made the standard assumption that this dm dE is actually flat. And if you assume that, you get the standard result just from the Kepler's law that basically after peak, the mass rate decay has to go as t to the minus 5/3. So people always thought of, if I want to find these objects, this t to the minus 5/3 should be a representative decay law for the luminosity. And what I'm going to tell you about is actually the implications of these DMDE, which we actually obtained self-consistently from the simulation. Now, things started getting extremely interesting when the core remains. Why? Because the core has its effective Hill radius. And it's actually going to influence these DMDE as the simulation progresses. So to illustrate this, I have this diagram in which I have plotted on this axis dEdn, which is the specific energy per unit mass, and here the energy. So you can think of this diagram, this is 0, so anything that is negative is bound to the black hole. Everything that is positive is unbound to the black hole. And you can see the symmetry in these plots, and the reason why it's symmetric is because the object is going in a parabolic orbit. Yeah? So about half the mass has to be bound and half unbound. And what I'm showing you here is for different betas. So when the encounter is weak, the pink region here is actually the distribution of mass that remains bound to the core, and you can see how it evolves. Yeah? And as it evolves, you do get some flattening, but of course DMDE is not exactly flat. And as you go deeper and deeper, basically you eradicate the core. This is a full disruption. And at the end, this assumption that Martin made, it's a good assumption because DMDE is actually relatively flat. And that's how you recover these t to the minus 5/3. But in between, the core actually drastically changes things. So what I show here is basically the rate of return to pericenter as a function of time for different betas. So this is where you basically shed a little bit of mass as you go to a full disruption. And just to give you a feeling why numerical simulations are so important, these are the analytical scalings that people got as a function of beta, and they're completely wrong. Yeah? And the assumption was made, particularly by Kochanik early on, was that you can think of the star as basically a frozen object, and then think about DMDE across that object, and then calculate it in a collisionless case. But actually, the fact that this object evolves, drastically changed the scalings. Yeah? And as you can see, we always converge at late times to these characteristics, t to the minus 5.
What happens if you take gamma 5/3?
Yeah, I can show you some of the... So we do that now, actually, this is the next. So we actually now do it for a wide range of structures and calculate what the peak and the decay. And there's slight differences. But of course, for lower mass stars, you have to do that. So that's what we do here. And this is basically the peak accretion rate as a function of the mass of the object. Yeah? So this is basically for rocky planets, white dwarfs, and basically main sequence stars. And basically what we can say is that all the scalings are correct and all the hydrodynamics are basically given in these functions. So the hydrodynamics depends on the impact parameter and the structure of the star, and we're able to predict. Now, something that you should notice is that the time of peak is in the main sequence regime is almost independent of mass. The argument is that these systems have about the same average density. And therefore, there's a lot of potential to actually learn about the black hole. Even if you don't really know what I call DMF, which is the disruption mass function, is, because the peak is actually so flat, and main sequence stars have very similar properties, you can learn about the mass of the black hole that got disrupted. That will strongly determine the peak. Okay, so we did the simulations of DMDT, and this is when I tried to give some credits to what we're doing. So this is the first pan-star event, and as you can see, it's beautifully sampled. Yeah? And we have actually taken our DMDTs, just the return of mass to pericenter, assume that the luminosity follows them, and as you can see, our curves capture the curvature amazingly well. Yeah? So what I'm going to talk about is what are the implications that the rate of return to pericenter and the luminosity match each other so well. Another important thing, as you can see from the light curves, is that there's very little color evolution. So the peak of this event is between 50 and 100 days after disruption, very constant color. I'll talk about how we can do that with a black body temperature of about 30,000 Kelvin, and it shows a clear dip after a peak, and then it sets up to this power law decay.
I'm sorry, where's that dip? I can't see.
So you go up, there's a dip, and then the power law changes. And if I actually showed you the derivative is very clear. I mean, if you look at this, this is the t to the minus 5/3 law, and this is much steeper. You can go almost to t to the minus 2.
So it's a dip in the slope.
Yes.
I mean, you framed it in the previous context, but how clear is it? There are no other explanations for this light curve.
Yeah, I mean,
go up and back.
let me actually give you all the details of the observations. But in principle, it was a center of a galaxy which was previously quiescent. He went by luminosity by a factor of 1,000, and he showed this light curve. Yeah. Now, the thing that it was actually quite interesting is that he showed these very strong, broad emission lines of helium, but he showed actually no hydrogen. If you take a, well, of course, if you know this, if you take a spectrum of this, you're going to see all of the absorption features that you don't see. So the spectrum is basically flat and consistent with a black body component. So yeah, the answer is not a supernova. So what the authors put forward, they say, oh, it has to be the disruption of a helium star. Yeah, and helium stars, are actually extremely, extremely rare. So we got worried about that. We said, well, what about, can it be a Wolf-Rayet star? Yes, it's made primarily of helium, but they're also extremely rare. Can it be a helium white dwarf star? Those are even rarer. And in fact, they're actually swallowed whole by a million solar mass black hole. And then something that was interesting is, well, could it be sort of an evolved star which in its first interaction passage got its hydrogen envelope stripped? Yeah. So we have done these calculations. What I show here is the self-bound mass as a function of dynamical time for different betas. So basically, this is how effective you're stripping the hydrogen envelope. As you know, when an object goes into the red giant, it becomes so much more vulnerable to tidal disruption, but the core basically doesn't even feel the tidal disruption. And then what you see is that even as you go deeper and deeper, a similar amount of mass compared to the core, in fact, remains in the system. And this is actually easy to understand because you can think of the envelope at some point when you started depleting it as an atmosphere. And as soon as you start trying to get rid of mass, the envelope collapses and it protects itself. So the issue is, yes, you can actually get rid of some of the hydrogen, but not all of the hydrogen. So we started thinking about, well, can a hydrogen-rich disruption actually work for this system? So the first thing, if you really want to understand where the emission lines come from, and this is more historically because a lot of work has been done, a lot of people thought, well, as soon as you...
Why are those lines so broad? I don't understand what's broad in the line. Your gas is at 30,000 Kelvin, so...
I'll show you where I think the broad comes from. I'm just going to argue that this is basically a broad line region with a system, in which basically the broadening actually comes from a quasi-hydrostatic envelope, and that comes from the average velocity of that radius. And there's basically a direct correlation of where those lines are formed and the position. So for a long time, it was thought that as soon as material returned into pericenter, form an accretion disk, it turned on the object, a lot of emission lines would be seen by those photons interacting with the unbound debris. Yeah? And we were worried about that because the unbound debris covers such a large range of densities that you should have expected to see these features of hydrogen that you don't see. But then what we showed using simulations is actually that the stream remains basically self-gravitating and it's actually extremely thin. Yeah? So the amount of solid angle that actually possesses is very, very tiny. Okay? And as you can see here, the unbound material actually remains basically self-gravitating. So the lines cannot come from this, and this comes from previous discussions that thought that the unbound debris actually provide a very large reprocessing surface, but in reality, it's almost like a thin spaghetti. Yeah? So the emission lines are not coming from that, so where are the emission lines coming from? So let me illustrate two simulations that we have done to try to understand actually how the accretion stream actually gets filled. So this is, you're going to see it in the orbital plane. Yeah. So what we measure is actually the rate of return to pericenter. Yeah. And as you can see here, there's a lot of hydrodynamical dissipation. I'll understand where it comes from. And then this material basically starts to circularize, and starts colliding with the stream and circularizing. And you get sort of a wide structure that is growing as a function of time as the orbital parameters of the material returning increases. Yeah? as you can see it here, while the abound material is basically going away. If you look at this perpendicular to this is basically the angular momentum redistribution region of the orbits. Yeah? And what you can see is that you're basically building this envelope around the black hole. Yeah? This is twice the tidal radius, which is the circularization radius of this material. Yeah? And material basically, as they're trying to circularize, because the orbits, the orbital parameters are increasing in semi-major axis, leads to this basically structure that is growing as a function. Yeah, so this is basically an accretion disk assembly from the inside out. These are different snapshots. So this is the narrow stream whose width is the size of the star, basically getting spread. There's there's a shock here that mediates the dissipation, and you're forming this structure. And as you can see, it can be rather optically thick and expanding as a function of time. So the way that we think about this system is that you have this elliptical disk that is being formed, and then you have this opaque reprocessing layer around it, and then you have this low-density material that basically ensheets the disk. And what we're thinking is that the lines are actually coming from this boundary, and this boundary is growing as a function of time. Yeah? So the physical model that we have for the broad line emission is that the emission is basically, the object is basically radiating, and the emission is reprocessing with this structure that is growing as a function of time. Now, as you know, in the broadline region, depending on the ionization of the line, things that have high ionization parameters, because the emissivity of the line depends on the intensity of the flux. Yeah? There's a characteristic, basically, location where most of the emission comes. And what we're arguing, basically, is that hydrogen is basically all fully ionized, and therefore that's what you're not seeing. Yeah? The region does not extend far away enough to actually hydrogen to be effectively produced. And this is basically what people in the AGN community basically argue. But as you go from lower ionization regions, you get a wider range of progressively larger size regions in which you see. And you clearly see a correlation of the full width half maximum with a lag. Yeah? So basically, all of these high ionizing species are basically deep into the potential, while these things are much farther away. Yeah? And if we're thinking of this as a truncated broadline region that's growing as a function of time. That's right. Let me show you the cloudy models. So you still have hydrogen as a coolant, but if you actually look at the emissivity of the line, yeah, which is given by these contours here in the cloudy models, basically that line can now get above the continuum. Yeah? And you can see it here. Wow. For example, helium-2, these are our trajectories of the mean density as a function of time, while the hydrogen is actually, the equivalent weight of hydrogen is within the 2 sigma of the line emissivity. Both the H alpha and H beta equivalent weight is very, very tiny. Basically, that's what you see. Yeah? And that's actually the basis of how the broadline region is actually produced. It's not that the hydrogen is not recombining, it's just that the emission feature is not strong enough. Yeah? The equivalent weights are small. And you can see it here, particularly in the H alpha. What are basically the flux, this is the flux and the density that you need to provide strong equivalent weights. Okay, so the way that we thought about tidal disruption was that the disk was sort of impulsively built. You get a disk that is truncated at twice the tidal radius and then accrete viscously. And what we're trying to argue is that that's really no longer the case. And if you actually do models in which you have a truncated disk, it gives you a terrible fit to the data. If you actually extend the disk, the fits certainly improve, but they're still terrible. And the reason why they're terrible is because this disk model produced basically huge color evolution. And what we're seeing is that there's no color evolution. Yeah? And now 2 more events from pan stars have actually been seen, and we see the same feature, that the temperature actually remains constant. So before I talk a little bit about where we think the reprocessing is coming, something that we were, James and I surprised is the overall decent match that we have of the light curve, just based on this simple dMdt models. Yeah? So we started thinking about, well, what needs to happen? In other words, what we're saying is that the luminosity follows the rate of return to pericenter, and that means that you have to have a strong dissipation when the stream comes back to pericenter, such that the disk forms, yeah, and then viscously accretes very, very quickly. Yeah? Now, the viscous time is actually relatively short, but the problem that everyone is facing now is where is the dissipation coming from? Yeah? From the material when it crosses pericenter, rather than going all the way back into this basically a long orbit. It actually has a strong basically sharing of the energy and starts forming the disk relatively quickly. How many time? So you can expect hydrodynamical dissipation. This is basically a simulation that shows this. Hydrodynamical dissipation is actually very, very important for lower mass black holes. The way that you can think about it is that the pericenter velocity, yeah, which is basically what gives you the kinetic energy of the object, is larger than the escape velocity of the star by the ratio of the black holes to the 2/3. Yeah? So that means that there's 10,000 more kinetic energy in a million solar mass black hole than binding energy. Yeah? So these shocks actually, for 1,000,000 to 1, hydrodynamical shocks are not very effective at actually dissipating the energy. So you have to rely on a different mechanism. And the mechanisms that you have are 3. One is the hydrodynamical dissipation. This is basically the mass of the black hole as a function of beta. This is the amount of dissipation that you expect per orbit. So hydrodynamically, or basically you expect sort of large dissipation for lower mass black holes, and then the dissipation is not very effective. There's a sort of MRI-like, because as the material comes in, if it's magnetized, you may expect some shearing, and this is under investigation. But what we believe it's happening is actually GR precession. So these objects actually if they get significantly close to the black hole, as these systems gone, with beta it's an order of the tidal radius, and the black hole is about 10 to the 7, then precession makes these objects actually cross. And since the orbit cross, there's a strong dissipation. Yeah? And what we believe is basically that dissipation is what it's helping circularize from very highly elliptical orbits to form a disk, and then the disk basically accretes viscously. Okay, so the simple model that we had in mind, and we did a MCMC Monte Carlo to try to see if we can derive the parameters of this, was we thought of it as we have an elliptical disk who has a certain scale, and that scale grows as a function of time, and circularization takes place, and we have basically an opaque photosphere which is reprocessing the radiation. Yeah? And we leave basically as a free parameter the size of the photosphere, and we try to solve for the kappa of the structure that we have. And this is basically our best fit model to the Y curve. You can see clearly here that basically what this reprocessing layer is doing is basically taking the disk emission and re-randomize basically that energy into a black body temperature, yeah, whose basically temperature it almost doesn't change as a function of time, and we're basically consistent with the Chandra limits. So what we're trying to argue is that not only you basically have to understand how the disk forms, but you also have to understand how these energies reprocess, because even though the luminosity is changing by 3 orders of magnitude, the temperature just stays constant. Yeah? So these are the fits. And you can see that you start having some distinguishing power, particularly in the black hole mass distribution. Yeah? Because the peak time, remember, holds information about the mass of the black hole. You can actually get a relatively good fit, or a good prediction for the black hole. And something that made me very, very happy is that the best fit stellar model is a star that you expect to be very close to the peak of the IMF, anywhere between 0.2 and 0.6, solar mass type star. Yeah? So the best sort of tidal disruption event that we have is actually representative of a black hole of about 10 to the 6, 10 to the 7, and a star that is a solar type star. And the reason why you didn't see hydrogen is that just the emission feature from the hydrogen is just basically weak. Yeah? The equivalent width is basically very, very small. Now, if we wanted to make sure that our or fitting for the photosphere was actually give us some consistent results. And as you can see here, the average opacity that you actually require to basically be consistent with the constant temperature is an opacity that is rather reasonable. Yeah, it's capped as about 0.5 to 4. And what actually we believe is actually maybe helium-2 is actually basically helping keep the photosphere about 30,000 Kelvin. Yeah. It's acting as a calorimeter, although we need to do more radiative transport calculations to really understand. But in addition, our model also fits really well the intensity of the helium-2 line in terms of imposition, because not only was the helium-2 line determined, but there was also velocity measured from the full width, equivalent width. And what you can see here, these are basically data from AGN, and we don't expect to see both the H alpha and H beta, and that's consistent with our model. The photosphere does something like that. Here's, of course, luminosity as a function of size. And what you see here is that the size of this structure is growing, yeah? But we actually don't expect to see hydrogen in this particular case. Yeah? And since then, there's another spectrum taken in which the helium-2 line has weakened, but there's no signs of the hydrogen. Okay, so the lessons that we're learning is that the disruption of a star actually produces this thin stream, and that thin stream does not contribute for the reprocessing of the lines, and that has very important implications, because what directly implies is that you're not likely to see this hydrogen, and therefore you don't need to make a star of pure helium to actually explain this event, which would have been really strange. So a helium-rich star is unlikely. The hydrogen is missing because it's mostly ionized, and the equivalent width of the line is just basically, cannot rise above the continuum. We have presented models of the fit and found that the disruption of main-sequence stars of solar composition is simultaneously consistent with the optical, the UV, the X-ray, and the spectroscopic data. You can build up a model in which you can actually explain all of those features. And that the posterior distribution resembles the priors that you expect for the IMF and the measured mass of the host galaxy black hole. And something that we're very excited about is this idea that when the number of these events starts growing, then you're actually going to be able to see the formation of these broad line regions as a function of time. And depending on the size scale of the black hole, it will give rise to different line emissions being produced. Okay, so just to illustrate that the future is bright, of course, once you go to something like LSST, you're expecting to see about 4,000 or so of these cascades. Okay? Now, someone brought up the idea that these systems can actually look like supernovae. And in fact, yes, if you only have colors and you don't have spectrum, it's very, very hard to distinguish the systems. Yeah? So particularly the Likert coverage is not very good. So what we're learning more and more is in those synoptic surveys, if you really don't have spectrum, it's going to be a very, very hard game to try to actually find these candidates and be making sure that they're not actually supernova, because the spectrum is very, very different in these systems. So for example, let me just give you sort of the distributions that you expect. This is basically if you truncate the distribution of M sigma, you say that actually dwarf galaxies do not contain black holes. This is where you expect in the black hole mass distribution for these objects to peak. If you only take giant galaxies, if you take all galaxies, the distribution actually goes basically to lower mass black holes, in which you expect a lot of the systems. And the first object that we detected is actually around here, which is basically the peak of the distribution, close to that of predicted by the giant galaxies. And there are some arguments to be made now that we have 3 events, whether or not this black hole mass distribution really extrapolates to lower mass. Thank you.
So thank you very much. Do we have questions?
So, 2 questions. One, if there is this narrow broadline region that's not giving H alpha and H beta, you also expect some other emission lines. Have you looked for these? I mean, I realize most of these are in the lines, but have you thought of trying to observe these in these events?
Yeah, I've been trying to convince observers that these are interesting events to follow. I mean, some of the problems that we have now with pan stars is that they don't make the data publicly available immediately. So that prevents other groups to do the follow-up effectively. But now they're very interested in actually doing these follow-up. And as you saw, the quality of the spectrum is not the best. I mean, the signal to noise is not great. But it is clear that the H alpha is not there at all. I mean, within like 5 sigma. But yes, you're right.
Can I ask another question? The other is that do you have a feeling for what the remaining core mass is relative to the original mass of the star for these objects?
Yes, I can give you an exact relation between how deep they go and how much mass remains.
Okay.
And that depends on the structure. Yeah, we have the functional form fits in our paper. I don't remember exactly. I mean, it goes very nonlinear, no, with beta. Meaning once you go from beta of like 1 to 3, I was telling you the disruption is between 1.8 to 1.9. So it's a very steep curve of how deep you go. But it also depends on the stellar structure. If you have a 5/3 sort of convective object, it changes.
Do you have any other questions?
If the star which undergoes the encounter is relatively massive, could its radiation pressure be important for the dynamics of the gas later on, or is that completely negligible?
Yeah, it's completely negligible. I mean, the first thing is, of course, because these stars are doing this random walk, which takes relatively long time. You don't really expect very massive stars to actually survive for long enough to actually be thrown in these radial Moscon orbits. They may get thrown out if they're if they're born very close to the to the black hole in a disk, and maybe some secular effects can do it. You are absolutely right that when the stellar debris isotropize at the scale of the tidal radius, the dominant pressure is radiation pressure. I mean, that is true. Because the object thermalizes. So, yes, I mean, things like, for example, rotation and initial magnetic field, initial rotation doesn't seem to matter very much, but the question of what happens to the magnetic field of the star, and whether or not when the object comes back, what happens to the stream, and whether or not you can trigger some sort of dissipation because of shearing is a very interesting question.
Do you have any more questions? Let's just
Is there any possibility of stacking these disrupting stars to create a model for AGN or quasars? I mean, I realize that you need to take into account the interactions between the stars, but is it possible that these are negligible enough to kind of stack them?
Yeah, so in the late 70s, I guess, Hills, which actually did a lot of work, postulated that if you take, say, half a solar mass and divide it by the tidal disruption rate, that gives you an average, m dot supply to the black hole. And he calculated that those black holes will be very close to the Eddington limit, and therefore all AGN activity in the early universe was basically powered by tidal disruption. And then Martin in '88 wrote a paper saying, well, that's not true because you do have half a solar mass, but you digest it in less than a year. So basically the duty cycle of these flares is very small, and the probability of you seeing an AGN active is very, very small. Okay? But it is true that once you get to the local AGN, where basically there's very little gas supply, whether or not the tails of these t to the minus 5/3 extended tails could in principle contribute to the luminosity function. And when people do these calculations, they say that maybe they could contribute to 10 or 20% of the total local AGN activity. So yeah, so people are interested in these tails and how they compete with other mechanisms like winds from the stars, feeding from the winds, and so on. So yeah.
Getting back to the question of the demographics of black
Yes.
holes. This is what we started with. What you predict for both the number and the observability must depend on what you assume about the structure of the stellar distribution. Right. So figuring out what number to actually assume for the velocity dispersion in a luminous galaxy is, what's the velocity dispersion called? Is so complicated in knowing what the stellar distribution function is.
Okay. Yeah, so for example,
Figuring out what, how fast you think it goes a lot.
that's right. So in the sort of early papers, people thought Dwarf galaxies that are not nucleated, for example, are not expected to contribute to the tidal disruption rate at all. So yes, you're absolutely right that the black hole could be there, but the stellar distribution is just so low, so diffuse that you don't expect them to contribute at all to the rate. So you're absolutely right. That's a very important parameter for the dynamics. It's also interesting that you can, because it's such a complicated problem, especially when you have a multi-mass component, you can turn around the question and see if you're able to basically start predicting what type of stars and black holes are more likely to get disrupted, then you start learning about the demographics of the stars and the stellar distributions of the system, and whether they happen preferentially in ellipticals versus in spirals and so forth. Yeah, but I agree that this is not well settled. You shouldn't believe these, just the order of magnitude estimates of the rate.
You predict a fair number of surviving cores that will escape the central region of the galaxies in some time scale. Are they, in some respect, different from normal stars in their observational characteristics apart from the dynamics? And is it hopeless or not to find those things?
Yeah, so I've been talking to Warren Brown quite a bit about how you can find them kinematically or not, and how long they actually last in these very radial orbits. So we have run some MESA models of the surviving remnants after the phase in which basically all that heat, and they go back to sort of like a main sequence like, and because their main, the mean molecular weight is different, their colors are slightly different. But not significantly different. And the question is, if you have a population that is spread in ages, and you're really trying to find difference in this, I don't think if you have the kinematics, just finding them by colors will be very difficult. The hope it will be, it would be great to find one of these really hot runaway objects, which you expect, but extinction is also very large in the galactic center, so maybe difficult. But we're thinking about it, so if you have any ideas.
Can galaxy-galaxy interactions, tidal interactions, increase the number of such orbits which go close to black holes?
Yeah, so there's now significant literature in thinking about black hole mergers, and particularly when the two black holes are on equal mass. The smaller mass black hole serves as a way of actually catalyzing these radial orbits, and it starts focusing these radial orbits very, very effectively, and you do get an increase in the tidal disruption. The argument is that the mergers are not common enough and don't happen often enough to actually just compete with the quiescent tidal disruption rate. But people argue, for example, if you see repeating flares of timescales from the same system, in terms of years or tens of years, then the only way that you can do it is if you have sort of a massive perturber actually focusing the orbits.
We did found several hypervelocity stars.
Yes. Yeah, so the argument of these hypervelocity stars is, well, the way that people think that they're produced is they come in a binary, and then you kick one at very high velocities. Now, the problem is that the kicks that we get from the systems are comparable to the escape velocity of the system. So it's only like 300, 400 kilometers per second. So you get them out of the sphere of influence, but not of the galaxy. And so when we did the Monte Carlo simulation in our paper, we show that still the tail of the distribution is dominated by binaries, but there's intermediate range in things outside the sphere of influence that is certainly dominated by these systems, and then you will need to combine kinematics and colors to try to find warrants it to be fairly optimistic that just kinematically you start finding a significant population is actually hard to produce otherwise, but it takes some time to eradicate those.
Do you have any more questions? Okay, then,
how long is the thin filament that's, the remnants of the star, how long would that be?
How long it will last?
Yeah.
So what's going to happen is that when the thin filament starts sweeping mass from the external medium and it sweeps the mass equivalent to its own, it starts basically accelerating, and it's probably going to spread there. And one has these hydrodynamical interactions with the... It may be the case also that because the hydrogen is initially completely ionized, and you start recombining at some late times, it may be the case that actually it starts spreading just because recombination energy injection into the debris starts being important.
But there wouldn't, for instance, instance, be the leftover little bit of one of these hanging around the galactic center?
Yeah, so Martin speculated in the 80s that there were these spiral features in the galactic center that they look like these kind of long spiral arms in the radio. That those could be basically the remnant of a tidal disruption that basically swept mass, started accelerating, and now expanded far away in orbit. Actually, produced that feature. So yeah, it will be interesting to see if one runs, a tidal disruption. I mean, it is interesting to notice that because the kinetic energy at the center is so high, the kinetic energy of the system is comparable to a supernova. So the amount of mass that you eject in a tidal disruption is actually 10 to the 51 ergs of kinetic energy. And of course, since it's a thin filament, it probably will take much longer for them to start accelerating. But there's some energy injection from that.
Bill, let me ask maybe the last question on the planetary aspect that you actually talked about. Did you investigate at all if it is actually different how you assume that the giant planet is structured, meaning core mass versus atmospheric mass, if that actually makes any difference in time scales and interaction?
Yeah, so something that we considered is basically how Jupiter's with cores. And then what happens in that case, if the planet gets into a very deep interaction with it, you actually get rid of the envelope. Yeah? And very similar to the red giant case, in which as much envelope you go, at some point, basically the star wants actually to collapse as it loses mass and it becomes actually protected to the tidal dissipation. And then our prediction is, if that's the case, there should be some super Earth objects left with an envelope, as basically the result of the tidal disruption of Jupiter. And depending on the mass of the cores, which are very uncertain, you can get a population of these systems that will actually tidally capture the envelope was ejected. And the same will happen with red giants. You do expect a population of sort of white dwarf-like systems in which the core survives and the envelope is ejected.
Any last questions? Okay, if not, then let's thank you.